Our topic is electron configuration. Electron configuration is the arrangement of electrons, or in simpler words, is the address of where the electron lives. The orbital sublevels are the probability map for the location of an electron. The easiest way to show the orbital sublevels is through the periodic table. The periodic table is divided into 4 different sections called blocks. There's an S block, there's a D block, there's a P block, and finally there's an F block. When writing out orbital notation, the S block holds 1 pair of 2 electrons. The D block holds 5 pairs of 2 electrons. The P block holds 3 pairs of 2 electrons. And the F block holds 7 pairs of 2 electrons. Each row of a certain block is labeled in numerical order, from top to bottom. The S block goes from 1s to 7s. The D block goes from 3D to 6D. However, the D block is 1 number off in comparison to the S and P blocks. The P block goes from 2P to 7P, and the F block goes from 4F to 5F. The F block is 2 numbers off in comparison to the S block and P block. The off-bow principle applies to the order of orbital sublevels along the periodic table. It goes from 1s to 2s to 2p to 3s and so on. The order will continue to snake down the periodic table. But however, once we reach 6s, the next sublevel will be 4f, and once we reach 7s, the next sublevel will be 5f. For example, if we were to start at 6x, the next sublevel would be 4f, then 5d, then 6p, and so on. The main basis of electron configuration is orbital notation. In other words, long form, unabbreviated. For example, let's use nitrogen. It has 7 electrons. 2 electrons would be placed in the 1s sublevel. 2 electrons would also be placed in the 2s orbital sublevel. For the 2p orbital, we'd have to follow Hund's rule and place 1 electron in each of the 3 parts of the sublevel before we can place a second electron in each part. In this case, there is no need to go around a second time. We now have a total of 7 electrons properly distributed between each part. Here's another example using boron that has 5 electrons. Our next topic within electron configuration is long form abbreviated. This form is written with the orbital sublevel along with the number of electrons in each sublevel shown exponentially. In this example, we used fluorine, which has 9 electrons. There are 2 electrons in the 1s, 2 electrons in the 2s, and 5 electrons in the 2p sublevel. Here is another example using magnesium, which has a total of 12 electrons. Next, we will discuss short form abbreviated electron configuration, in other words, the noble gas shortcut. In order to shorten the electron configuration, we can use the nearest noble gas with a lower sublevel to said element as a substitute for the previous sublevels. You would then add on the following sublevels in order to reach the appropriate number of electrons. This example uses chlorine, which has 17 electrons. The noble gas closest with a lower orbital sublevel to chlorine is neon. First, you'd put the element symbol for neon in brackets. Immediately following the noble gas would be the remaining orbital sublevels required to reach chlorine's number of electrons. When naming the remaining orbital sublevels, the number of electrons in each should be written like an exponent. Here's another example of short form abbreviated electron configuration using cesium, which contains 55 electrons. Our next subject of electron configuration is Hund's rule. It states that all orbital sublevels within multiple pairs of electrons need to have the electrons in said element dealt like cards. This means no one pair of electrons in one sublevel can be filled until all of the pairs have 1 electron occupying the section. This picture shows how the electrons are spread evenly before adding more electrons into each pair. Our final topic within electron configuration is the Pauli exclusion principle. This principle tells us that only 2 electrons will be able to fit into a pair within a sublevel. An upward pointing half arrow is used to show one electron. An upward pointing half arrow and a downward facing half arrow are used to show two electrons. This also means that the pair is full. This visual can help us understand this topic because it shows multiple things. The two arrows show that the pair is full by using a stop sign to explain that the section cannot hold any more electrons. It is saying stop, so no more electrons can go into this pair. The one arrow shows that the pair can hold one more electron by using a green light to explain that more electrons can be held in this section. In all, electron configuration can be written in many different ways. These ways are shaped by different rules.